Hi and welcome back to Data Garden. Thanks for checking out my video. I hope you're doing very well. Today we are back with the XGBoost machine learning algorithm, and we want to build up on the regression problem from the last time. This time we want to implement the algorithm in the Caret package, which gives us some nice options for testing our algorithm automatically and optimizing the different parameters that XGBoost is offering to us in order to make the algorithm more powerful or also more restricted depending on what we want to have. First of all, if you haven't followed the previous tutorial, then I will put the link to the video down below, and I will also put the code down below so that you can start right here if you want to. As the second thing before we start, I will try to optimize this a little bit so that it doesn't take quite as much time. But if you do this with 10,000 observations as we're doing now, be prepared to be waiting like 1 hour or 2 hours depending on what kind of computer you have, because it really takes quite a long time for the algorithm to optimize everything. Okay, with that in mind, let's get right into it. So the first thing we want to do is I want to reduce the size of the data frame that we're using from 10,000 to just 1,000 so that everything takes a little less time. Consequently, we also have to limit the dataset size here for the training and testing to 1 to 500 and 501 to 1,000. Okay, having done that, let's run all the code from last time again. And we see that we got 2.7 RMSE from the linear model and 1.8 from the XGBoost model. Now, if you remember correctly, the last time that we used the XGBoost algorithm with 10,000 observations, we had an error of 1.2. That could be, of course, that our parameters are wrong for this smaller data set. But it is also the case that this algorithm, it ideally needs like a lot of observations to really learn the best. So keep that in mind when you want to employ it. But now let's get into the proper optimization, and let's load the Caret package that we're going to need in addition to the packages that we already have opened. And that will be install.packages, and the name is Caret, C-A-R-E-T, and it's one of the best machine learning algorithms for R that are available. Now, as you know, I'm a big fan of type equals binary, but you can also install the self-compiling package if you prefer to do so. Okay, I already have the package, so I will go straight ahead and use library Caret, and I had already loaded the library from my preparations. If you load it the first time in a session, then I think typically it will tell you something like that it already also loaded the packages lattice and ggplot2 as well, which Caret depends on those. Okay, now we can start by defining our new learner, and that will be, I guess we will call it XGB underscore Caret, and we assign that that name to an object which we define with the command train from the namespace Caret, as you see here. And now we have to define a whole bunch of parameters. Here it so kindly tells us that we have to define x, but that will not be quite enough for it to work properly. But yeah, first we have to define x, which is the data set that contains all the independent variables rather. And one advantage of Caret is that it can deal with the data frame structure, so we don't have to feed it the XGBoost dense matrix from the last tutorial. We can just do training, but then we have to make sure that we only feed it the columns 1 to 10. So we have to type comma 1 to 10 to select all rows, but only columns 1 to 10. After that, we type comma, and then we define the y value, which will be training $y. After that, we have to define the method. So Caret is a like almost universal machine learning library, and it has several dozen different algorithms from which you can choose. And you can choose the algorithm that you want to use with the method command here. And in this case, we want to use XGB3 with a capital T. There is also XGB linear, which we can use, and I think we will get to that in the next video of the series. So after that, type comma again. And one thing that I want to do, which is not mandatory, but I recommend it, is that we define the objective function. And in this case, I want it to be reg colon squared error. So what this simply means is that we have a regression problem and we want to minimize the squared error. Now we have to define two more things, and that is the train control and the tuning grid. Let's go with the training control first. So that will be tr control equals, and now we have to put a function within this function, which will be train control, also from the Caret package. And what this allows us is to specify how we want the different tuning parameters, such as en route and eta, to be tested. In this case, I will choose a method of repeated CV with a number of let's go with 3, and repeats of 2. So what this means is, I will only explain quickly, I think. Repeated CV is repeated cross-validation. So what cross-validation means is that you split the full training data set into, in this case, 3 parts, that is the number, and you always leave out 1 and take 2 for the training, and then you predict the model on the one that you left out. And you do that 3 times in this case, of course, but then you repeat the whole process 2 times as well, with different splits for within your training data set. Okay, and then I want to implement one more command here, so we type one more comma after the 2, and that will be verbose eta equals true. So what that means is that for each iteration of the training, it will give you a remark of where it currently is, so that you kind of have an idea of how long it will still take. So then after the first closing bracket, we type another comma and we specify the last part command of this train command, and that will be tune grid with capital G, and we will define that as another command, and that will be expand.grid. And here we define the values which we want to test for all the different hyperparameters. And we have to define at least 7 hyperparameters for this XGB3 algorithm, otherwise it will not work. Now we already know 2, which are n rounds and eta, and we're going to start with those. So that will be n rounds, and that will equal a vector with the values, let's try 500, 1000 and 1500. I'm going to explain why I choose these values and what they mean later on. So I will first type everything, and then we have to wait for quite a while for the algorithm to execute. So that's why I'm doing it this way. Then we define the eta, and I will try 0.01 and 0.05. Then we come to the parameters that we haven't used so far, And the first one will be max underscore depth. Yes, like this. For that I want to try say 2, 4 and 6. Then the next one will be call sample underscore by tree, and for that I want to try 0.5 and 1. And next one will be subsample. For that one I also want to try 0.5 and 1. Then we still have gamma, and for that I want to try 0 and 50. And finally we have min underscore child underscore weight, and for that I want to have 0 and 20, let's say. So now we have everything, and I will press run and hope for the best that I've done everything right. And that looks good, and it also goes kind of quickly with just 1000 observations. So you can see here that it's trying out one combination after the other of all the combinations of 1500, and then first 0.01, 2, 0.5, 0.5, 0, 0, and then 1500, 0.014, and so on. You get the idea. So while we're waiting, I'm going to explain to you a bit what these different parameters mean. The number of rounds we have already established in the last tutorial. That is how often the algorithm will iteratively try to improve on itself, on the results of the last round. And higher generally means that the algorithm will be more complicated, more fitted to the training data. It will include more information, but it might also include useless information that actually diminishes your predictive performance. The eta is how quickly the algorithm will learn with each observation, or not with each observation, with each iteration rather. So a higher value will mean that the algorithm will fit more quickly. A lower value will mean that it will learn more slowly. So of course, if you have a lower value for eta, you need a higher value for n rounds, and vice versa. Max depth, that's the maximum depth that the tree will grow. So with 2 it will make like 2 layers of branches, so to say. With 4 already 4 layers of branches, and so on. So this is probably the most important layer, most important attribute to change the complexity of the tree. Because if you have a tree that is very deep, let's say with a maximum depth of 10, then the algorithm will be a whole lot more complicated than with just the depth of 4. And of course also if you have a higher depth, then this will mean that you will need less rounds, and vice versa. But typically, at least it's my experience, that you should rather try lower amounts of depth and higher amounts of rounds, and you will get better results with that than with higher depths and lower rounds. Call sample by tree, that is, the call stands for column, and it basically means with each tree that is built, only part of the columns that the whole training data set has will be considered. So in this case, either exactly 5 columns or all of them. That's what we're going to try out, which is better. And this can help to kind of get more information from each column by limiting kind of throwing some columns out for each test and seeing what happens. The same you can also do the other way around with the rows that you have in your data set. That's the subsample command, where each tree will use either only half of the whole observations or all of them. And that is quite good, especially if you have an imbalanced data set, because yeah, you will like kind of randomly sample some of the rows, and you will maybe have more of one type in one sample and more of the other type in the other sample, and it helps with the precision of the algorithm quite a bit usually. The next one is gamma, that is the minimum loss reduction. So in other words, if the value is 50 here, then it means that we have to reduce the squared error by at least 50 in order to make a new move. Otherwise, the continuation of the tree will just not be built. And that is a very potent mechanism to limit the overfitting of the algorithm on the training data. So if you have a problem where your algorithm is really good on training data but really poor on test data, on new data, then a good hint is to put the gamma up. The final one is min child weight, which is the minimum, like a minimum weight that a final branch of a tree has to have in order to be created. So there has to be a minimum number of observations kind of that have to be put into a decision branch in order for this branch to be created. Otherwise, if there's, in this case, like less than 20 in it, then the algorithm says, okay, this is not significant enough, I will not do this. Now, how did I come to these values that I've just entered here? To be honest with you, I have just entered them by my intuition. I have been using this algorithm for a bunch of different problems already, and after a while I kind of got a feel for what are sensible choices. Now, I have to say, if I would want to really optimize this to the perfection, then I would also choose quite a lot more different parameters here. But you can see I'm already talking for a couple of minutes here, and we're only at repetition 2, fold 1, so we still have fold 2 and fold 3 ahead of us, and I don't want to make this longer than necessary for you. So that's why I've chosen these parameters. Okay, I think I will stop the recording for now until the training is done, and then I will be right back with you. Hold on, it's only a short way to go. Okay, so in the meantime, the training of the algorithm is done for me, and as you can see in my case, the final parameters are the number of rounds 1000, a maximum depth of 2, the learning rate of 0.05, gamma of 0, call sample by tree of 1, minimum child weight of 0, and subsample of 0.5. You also see that in my case I have these 50 warnings here, which have to do with the objective function. If you get these warnings as well, I think it's safe to ignore them. Depending on which version of R and Caret you use, they may or may not occur for you. So what we want to do as a final step is, again, create the testing error and see how it compares to the native implementation of XGBoost that we used at first. So we create a new column in the testing data set, so that will be testing $error XGB underscore Caret, like this. And what we want to use is, we can use the predict function, and our model that we want to predict with will be XGB Caret, and the new data will be testing and in square brackets comma 1 to 10. Press run. Okay, that works fine. Testing $, I did a mistake there, of course. It's not error, it is pret XGB Caret. So press run again with the new name, and then error XGB Caret. That will be testing $pret XGB Caret minus testing $y. And then our mean testing error will be mean of testing error XGB Caret, and that is 0.10. And the mean, the root mean squared error, that will be the square root of the mean of testing error XGB Caret squared, and that is 1.479. Now let's go back to the native implementation. That was 1.79, so we still managed to reduce the error by quite a bit. Let's calculate the ratio here very quickly. So only 82% of the error of the native implementation. I think that's quite an impressive jump that we were still able to make with parameter tuning. And keep in mind, here, for example, we are still at the border values sometimes. For example, with the max depths, we're at 2, so technically we should still test out 1. With all of these values, we have only defined 2 options, so probably it means that there are still better options out there. For time reasons for this tutorial, I limited the search to these options here, because I just want to show you how it works and kind of what these parameters mean. But if you're interested, then why don't you go and continue after this tutorial and maybe test out a few more parameters based on what we have just done, and show me down in the comments how far down you can still push the error on this data set. I think that would be very, very cool to see, and I would love to hear about your solutions. So I hope that you have found this helpful. In the next tutorial, we will be talking about the XGB linear algorithm instead of the tree algorithm. So I hope that you will join me for that as well. If you do, then see you next time. Until then, have a great time. Thanks for watching, and bye-bye.